Let us discuss the question from strength of materials. So you have a column of circular cross section which is fixed at one end. So this is fixed at one end and free at other end. So this is basically the column. Now the length L is given. So a horizontal force when you apply, it says it deflects. Okay, this is basically the deflection, and the delta, let's say, is the deflection. So then in that case it will be just like a deflection of beams. So it's something like this: you have a horizontal column and you apply a force, it gets deflected by delta. So when you apply, it's just like a cantilever beam, and when you apply a point load, it is FL cube by 3EI is the deflection which we get from the double integration method. So the same thing can be used here, FL cube by 3EI. Now delta is given as 0.05 L, and that is equal to FL cube by 3EI. So the L square will get cancelled. So what we get is 0.05 into 3EI by L square, and that will be 0.15 EI by L square. That is my F. Now there's a question that now the other part is that he's applying the horizontal load, and at a point when this becomes the critical load. So the critical load would be, for this problem, the critical load is EI by it's basically pi square EI by the effective length for this boundary condition when one end is fixed and the other end is free is 2L. So 2L effective length whole square, so it is 2L whole square. So pi square EI by 4L square. Okay, so now what they want is, they want basically the ratio of this P critical by F. Okay, so pi square EI by L square, and F is 0.15 EI by L square. So this is basically pi square. Okay, so this will be 4L square. Okay, pi square EI by 4L square, and then 0.15. So it's pi square by 4 into 0.15, so it's 0.6, basically pi square by 0.6, and that is basically when I multiply it, I get 16.44. So this ratio is basically about 16.44. So the answer is about 16.44. It's just a combination of deflection of beams and the critical load. Thanks.